everyone. My name is Jared Longfox, coming at you from the University of Central Florida, Department of Physics, in lovely Orlando, Florida, USA. Today, we are lucky enough to have Dr. Kathryn Hadler of ESRIC, the European Space Resources Innovation Center. She has her own intro and everything, so I don't need to keep talking, but just a few logistics that regular attendees know well for those of you that may be new. We will be taking questions at the very end. At the bottom of your screen, at least how my Zoom window is laid out, there's a Q&A button. It looks like a little speech bubble with a question mark in it. You can click that and punch questions in as we go, or wait till the end. I would do it as we go because when Kathryn's talk is done, we'll be taking them in the order received. And also, it was brought to my attention, last note, one of our faithful attendees let me know that they registered for this and didn't get the link to join for a couple hours after registration. If anyone's had that issue or has that issue in the future, let me know. I can have AIAA look into it. It was probably just a communications or internet traffic thing. I don't know. But let me know if there's any troubles, as always. So with that, I've talked enough. Kathryn, please take it away.
Thanks, Jared, and thanks for the invitation to speak. Let me just share my screen. I can't do two things at once.
I do see it already.
Oh, you see it already?
I
great.
do.
It's because it said it had green share. It's a good start. Thanks, Jared, for the invitation to speak is part of this webinar series on space resources. So my name is Kathryn Hadler. I'm the director of the European Space Resources Innovation Centre, ESRIC. I'm coming to you from a rather dark and gloomy Luxembourg. So good morning, good afternoon, good evening, wherever you happen to be. So I am going to talk today about the work that we do at ESRIC, the research that we do in space resources in ISRU at ESRIC. We celebrated our 5th birthday, ESRIC, last week. So we're going to cover some of the activities that we do in terms of our research. But firstly, I thought I would give an introduction to me. Because I don't come from the space sector, I am not an aerospace engineer. So my background is that I am a chemical engineer. I spent about 20 years, giving away my age, working in flotation, froth flotation, which is a mineral separation process used at huge scales in the mining sector to separate minerals based on their surface properties. And I did trials all over the world in flotation plants around the world. So those photos that you see are my happy place in steel toe cap boots and overalls carrying buckets on mineral processing plants. This is my background. I became involved in space resources in ISRU in around 2018, which is when the European sector really started to move. And we're obviously in the US that NASA had been doing this for a long time, but 2018-19 was really where we saw a lot of movement in the European community. And I've been at ESRIC as director since 2022. So firstly, ESRIC and Luxembourg. Why are we in Luxembourg? Why am I in Luxembourg? Well, Luxembourg really put itself on the map in 2016 with the spaceresources.lu initiative. So this initiative was government-led, and it was really about economic diversification for the future, looking for future economies. And so this initiative really prioritized space resources as something that Luxembourg should be interested in. This was followed in 2017 by the Space Resources Law. So Luxembourg was the second country in the world to have a law relating to the use of space resources. And then the creation of Luxembourg Space Agency followed in 2018. And this was followed in November 2020 by the launch of ESRIC as the world's first research and innovation centre entirely dedicated to space resources. ESRIC itself, as I said, it's an initiative of Luxembourg Space Agency and Luxembourg Institute of Science and Technology, LIST. So those are our two main funding bodies. And we work in strategic partnership with the European Space Agency. So we are not part of the European Space Agency, but we do work in partnership on several different initiatives with ESA. Luxembourg itself has really grown its space ecosystem over the last 10 years or so, and now there are around 80 space organizations, not all space resources, but in space in general. So it's a really dynamic ecosystem and a really lovely community. So about ESRIC, who are we? What do we do? Well, we have a very clear mission, and our mission is to be a world-leading centre of excellence in the science, technology, and business of space resources to support a future in space economy. So we are here to do everything to do with science, technology, and business related to space resources. And the work that we do then is split into 3 different pillars. So we do research. We have our researchers, and this is really what we're going to focus on today. So we're developing our capabilities and our laboratory facilities, but we're also developing facilities for the community to use, and this is in partnership with ESA. We support startups and early stage ventures through our commercialization activities. And here we run an incubator and a business accelerator. And this is one of the activities that really makes us unique in the world. And then finally, we run our community activities. So we run a challenge, the ESA and ESRIC Space Resources Challenge, but also the annual Space Resources Week event. So if you're not sure, Luxembourg, it's a small country, about population about 650,000. And we at ESRIC are located about 20 kilometers southwest of Luxembourg City, right on the border with France, in an area that's an old repurposed steel refinery. So we have these lovely blast furnaces nearby. Our building currently is just to the left of this image. We moved in summer. So just to the, you can just about see it here. This is where our building is to the west. We are currently a team of 30 people, and this includes 7 PhDs, 7 postdoctoral researchers, 5 researchers who have more experience, 3 engineers, commercialization specialists, a community manager, and so on. So we're a pretty big team, and we cover a wide range of disciplines. Much like space resources, which is an incredibly broad field, we as a team also have academic backgrounds in many different fields, from planetary science and geology through to material science, aerospace engineering, mechanical engineering, and of course, chemical engineers. And chemical engineers, as I am fond of saying, are the best kind of engineers, very useful chemical engineers. In terms of growth, we've been growing. At the bottom right-hand corner, you can see the growth of ESRIC since we launched in 2020. I like to say this is a kind of a publicly funded institutional level of growth. So for many of our startups and scale-ups and people moving the private sector, then we see much more rapid growth. Here in the publicly funded world, I think that constitutes a very steady growth over the years. But let's take a step back. We've looked at ESRIC and the Luxembourg ecosystem, but actually let's take a step back in the European perspective. So what's the European perspective on this? I said earlier that that I joined the community, the ISRU community, in around 2018-19 when the sector in Europe really started to move. And this was linked to activity driven by ESA. So in 2019, ESA published its first and only space resources strategy. This is really important at the time. It's publicly available. You can find the space resources strategy. And what you find in that document is that the focus is very much on oxygen extraction from lunar regolith. There's talk about understanding resources, on understanding volatiles, but in terms of technology development, the focus is clearly stated on oxygen extraction from lunar regolith. And then if we fast forward to 2024, then ESA last year published a new space exploration strategy called Explore 2040. Now, this strategy It covers all aspects of exploration, but in terms of space resources, the focus is explicitly stated on prospecting. So here we can see the focus, the near-term focus for ESA is on prospecting and characterization of lunar resources for future use to support space exploration. And these 2 points are very important, as we'll see. The ESA ISRU initiative has 3 key areas of activity. So this is a group, this is an initiative at ESA, and they define their interest in ISRU in 3 areas, and that's technology de-risking, market de-risking, and community engagement. And then within that, there are pillars. So we see ground-based research facility, development of ground-based research facilities, technology de-risking, prospecting and data modeling over in pillar 2, space resources challenge, business incubation, acceleration and modeling, community events, and in situ demonstrators. So these are identified areas that ESA is actively supporting in order to support the European space resources activity. And you can see that actually 5 of those are really where we also work in ESRIC. So we cover 5 of these key events. But now what I'm going to focus on for the rest really is, for the bulk of the time, is the research that we do. The research that we do at ESRIC, space resources, as I said, is a really, really broad field. We cover so many disciplines, and there's a need to focus. When we're starting anything up from the beginning, then we need to focus on specific research topics. And so really the ESA perspective, so the lunar oxygen extraction side and the prospecting is really what drives our research strategy. So if we look at the work that we do in terms of research, we have a prospecting area. So here we look at resource mapping and prospecting strategy. I'll talk more about that shortly. And then we look at oxygen extraction from lunar regolith, which involves handling of lunar regolith, extraction, looking at reduction by hydrogen and molten salt electrolysis, and then purification of the products. We're also interested in construction. So here specifically, we're looking at sintering and melting of the lunar regolith, and then more broadly at the system level activities. So modular design, process simulation, and evaluation of process routes when we look at the system, but also for the environment. So environmental impact, recycling of equipment, and dust mitigation. And then because we must keep focus in space resources, there's so many things we can do. There's a lot to do in this field, and there's so many areas we can focus on. It's useful to really think about what are the products. And so here in this diagram, the target products that we are interested in are oxygen and water, whether it's produced water from hydrogen reduction or extracted water and oxygen, metals that we can extract from the lunar regolith, and construction. These are really the target products. Everything else here is a means to get to metals, oxygen, water, and construction products. And that's very important to keep in mind that we're trying to get to, based on the resources that we have, we're trying to get to products that we can use. And this is really the key importance of space resources. For a resource to be useful, it needs to be recoverable. So we need to know about the resource itself. We need to know about its form, what form it takes, what are its properties, its size, and so on. But also we need to understand the potential technology we're going to use to recover that resource and turn it into something that's useful. So we need to understand what the operating windows of each of those technology units is, and how they link together in systems, and how that relates to the properties of the resource itself. And that will give us our system for extracting and using resources in space. So in terms of prospecting, I said there's 2 key areas of focus now. So we've got prospecting on one side and oxygen extraction from regolith. So specifically in ESRIC, what are we doing in research related to prospecting? So in prospecting, we are looking at mapping and characterization of space resources. And here there's two areas. So on one side, we've got the resource mapping. So this is where the planetary geoscientists are really happy and are very in their playing to their strengths. And then over here, we have in situ measurement. And in situ measurement, we also look at instrument development and sampling strategy. So in terms of resource mapping, what are we doing? Well, currently we've just started a project with ESA, with the European Space Agency, that will develop resource reports that will consolidate data and information related to specific resources. So, for example, water ice or rare earth elements, so that we can say, okay, this is what we know about any given resource, and these are the gaps. Because by understanding the gaps, we can understand which data we still need to acquire in order to be able to characterize that resource more fully in terms of deposit size, form, and other characteristics. So this is a project we've just started, really looking at, like I say, using the existing data and consolidating this in a way that allows us to identify data gaps and limitations in our current data sets. But on the other hand, in terms of in situ measurement, we have a project with the University of Brno in Czech Republic to develop LIBS, that's laser-induced breakdown spectroscopy. So this is an in situ measurement that will give us elemental data for lunar regolith, and this is currently we are developing this with a postdoc that we have at ESRIC. But also we're looking at sampling strategy, and I'll talk more about this shortly. In terms of mapping and what we can and can't say about resources, one of the projects that we did with one of our experienced researchers is Abigail Calzada-Diaz, who's a lunar geologist. So she's a specialist of lunar geology and previously worked at iSpace. One of the interesting features, what can we say about our resources and the form that they take? And so here she's interested in ilmenite. Ilmenite is iron titanium oxide, FeTiO3. The reason that we're interested in ilmenite is one, because it's an interesting potential resource, potential area where we find concentrated amounts of helium-3. So there's a link between ilmenite content and helium-3 concentrations, but also because, as we'll see as we move through the slides, ilmenite is important for oxygen extraction. Specifically for hydrogen reduction. So there's two reasons why we might be interested in regions of high ilmenite content in the lunar regolith and the form that it takes. So what Abigail did in this project is she looked at areas with high concentration of ilmenite, so over 9 weight percent, and looked at the genetic models for that ilmenite. So what was the origin of the ilmenite? And then through this process, through this geological mapping process and the definitions, and she was able to identify 3 different likely origins of the ilmenite. And this is important because the form that the ilmenite takes in the regolith may be linked to its origin. So when we talk about form of the ilmenite, what we mean is what's the size distribution within the lunar regolith? Is the ilmenite concentrated in a larger size distribution or finer particles? What is the content? What is the shape, the other properties of the regolith that we find, where we find this high ilmenite content regolith. So linking the origins of the ilmenite to the form is important, because what we want to know is the form of the ilmenite for developing processes further downstream. If we know that the ilmenite from a specific origin happens to be present in larger sizes, larger particle sizes, then that's important for any subsequent processing because it allows us to define our process routes. So understanding the origins and linking that to the form allows us then to link that to our eventual process routes. But it's also important to note the scale of the moon. I always find any excuse I can to throw this slide into a presentation. Um, so because I really like the scale. I mean, we look at these maps of the moon and we accept we accept them. It's fine. Look, we can see all these different types of mare basalt that have been identified, so on. But when you look at the scale of the moon, the features of the moon are not small. So on the left-hand side here, you see Shackleton crater at the lunar south pole, which has a diameter of 21 kilometers and is 3.2 kilometers deep. And on the right-hand side, you will see this is Bingham Canyon. This is a copper mine in near Salt Lake City. It's one of my holiday photos. And this is 4 kilometers wide and 1.2 kilometers deep. It's a huge hole in the ground. This mine actually used to be a mountain and they started mining 120 years ago and then got deeper and deeper and deeper. And then you end up with a hole in the ground that's about 1.2 kilometers deep. The trucks that you see on this carry about 250 tons of ore or thereabouts. And then you can see some pickups behind. So the scale of this is huge. And the reason that I'd like to throw this slide in is because it really reinforces the scale of the moon. These features are not small. And in many cases, they're larger than some of our very large mining features that we see on Earth. So it's useful to keep in mind when we are considering prospecting, exploration, and future operations. But the lunar regolith itself is really complex. I know that Josh Rosera gave a talk in this webinar a couple of months ago. He's one of my PhD students from my previous life when I was at Imperial College London. He was my first PhD student working in space resources. So this graph is from his review paper on beneficiation. The reason that I put this slide in here is we talk a lot about the regolith. I've talked about particle size distributions. And we know that the regolith is very fine, it's very abrasive, it's very electrostatically charged. But we take this graph and we say, okay, well, the average particle size is around 72 microns, 60 to 72 microns. But actually, our knowledge of the composition of the regolith is from remote sensing and also from the return samples. But our knowledge of the particle size distribution is only from return samples. And it's worthwhile highlighting that the samples that were returned during the Apollo missions are not representative. And so currently in ESRIC, we're doing a huge amount of work on representativity. So here's another example. This is one of my PhD students, Xiaochen Zhang, put this together. This is a compilation of the size distributions of some Apollo samples. And really here, I know that it won't be very easy to see, but the most important thing is that the purple bars are the particles that are less than 1 millimeter, and the blue bars are those that are over 1 centimeter. And anything that is not purple is over 1 millimeter, obviously. But what this shows across these samples is the range of particle sizes. So often with simulants that we use in our research to test technologies for space resources, often they have particle size distributions where pretty much 100% is passing 1 millimeter. Over the last couple of years, we see more and more simulants that have a larger particle size distribution, which is very good to see. But actually, across the Apollo samples, there's a huge range of particle size distributions. And to understand that, you need to go back into the data sheets to understand how that sample was taken and its origin and how it was subsequently handled. And this we really need to be careful about understanding where our samples come from so we can understand how to use the data. So like I say, this is something that we're working on a lot at ESRIC at the moment. And we've been evaluating sampling tools and approaches that take into account sampling statistics and representativity. So currently there's a postdoc, Serena Peroni, and PhD, Joe Witchells, who are looking at sample representativity. Now, sampling statistics doesn't sound much fun, but actually it's really important because when we're looking at resource mapping and mapping for resources, then it's a more systematic approach than space exploration, conventional space exploration, where we're looking for interesting features. Here, we're not necessarily looking for interesting features. but understanding the distribution of any resource of interest over a certain area. And for that, we need something that is more systematic. So we need to understand the likely sources of error in sampling, which you can see on the left-hand side, and then the sampler that we developed, which is the table on the right-hand side, how the errors that might be incurred from any given sampler design. So this is from a recently published paper. I think it's in press at the moment, but we can see that it starts to become important. If we want to take samples, then that's very interesting. But if we want to map resources, we need to take a different approach, and the strategy becomes very important. So moving on to lunar oxygen and metals production. So in terms of oxygen and metals production, I've said already, the two processes we're interested in at ESRIC are reduction by hydrogen here and molten salt electrolysis. So these two processes both have different temperatures requirements, feedstocks, and so on. But in both cases, they will benefit from some kind of control of feedstock going into the process, and that's where regolith handling and beneficiation comes in. Obviously, this is my field of expertise, so I think it's the most important part, the beneficiation, but I know that not everybody agrees with this. So we've got hydrogen reduction, molten salt electrolysis. Before this, we need some kind of control on our feedstock, so we have confidence of what's going into the reactor in the first place. And then afterwards, we'll need some kind of purification and capture. Here, we're looking at adsorption in partnership with Air Liquide. But in addition, like I say, we also look at other aspects as well, such as dust modeling. So we're using discrete element methods to model dusts in enclosed spaces and hardware recycling. But for now, we're going to focus on this left-hand side of the diagram. So let's start with dry size classification, because if we're going to do any kind of controlling of the lunar regolith, then we will need to do this dry, of course, as you would have learned from Josh Rosera a couple of months ago. This graph here is from a PhD student of mine from Imperial College a few years ago who was looking at dry cyclones. So we're looking at gas cyclones. But the review itself was very neat because it characterized all the different types of ways that you can separate particles by size dry. And really what we see is that many of these size classification technologies are better suited to larger particles. So if we go back to our size distribution, the average particle size distribution of lunar regolith is around 60, 70 microns. So we're in this kind of region here. But we see that many of these are better suited to high throughput and larger particle sizes. And really where we're operating is down at this level here. So we're operating right at the bottom of that graph. Low throughput, so very small flow rates, and a really wide particle size distribution. So if we're going to think about designing anything that will control particle size of lunar regolith, then probably starting with something based on centrifugal force might be a good idea. Also helps with the low gravity of the moon. So this is exactly what we're doing. We're developing a spinning cone-based particle size classifier. Now, this technology isn't new. It has been tested before. There was some research done by some Australians and also in NASA. But what we're looking for specifically is design considerations and also predicting whether we can predict the performance of this classifier in low gravity and under vacuum. So the principles of this spinning cone classifier are pretty simple. You have a spinning cone, you feed the regolith onto the spinning cone, the larger particles will fall off first, and the smaller particles will travel round. So if we look at the force balance of this system, it's a mixture of centrifugal force, but also friction. So the large friction element in the behavior of the particles. And you can see, let's see, hopefully this will work without being too glitchy on your screens. But on the right-hand side, this is an example of how it works. There's a spinning cone. The particles fall onto the cone And those large particles you can see to the left of the image are falling off. They're bouncing all over the place. And the finer particles will travel around the cone as it spins. There are many, many, many variables in this system, and we're currently looking at ways to optimize it. So we're taking an integrated approach to this. We've developed a single particle force-based model. We're using discrete element modeling methods for DEM for simulating multiple particles, and we're doing the experiments as well. And this is so that we can understand, firstly, the operating window. What particle size ranges does this system work for? What's the minimum size that we can separate particles at? Can we get down to those really troublesome 50 micron particles? But also, how does it work under low gravity? How does it work under vacuum? On the left-hand side here, you can see some examples of what happens to finer particles and larger particles when you put them on the classifier differently. So we understand this from a fundamental level. Where do the particles fall? How can we control where they fall? How can we separate those particles? And this illustrates very neatly. So on the right-hand side, we've got larger particles that fall off. You can see fall off sooner. And then finer particles on the left-hand side, and they travel further around the cone. The bottom is a Highland simulant, and the top is a glutinate type simulant. So this is more angular particles, and you can see with the more angular particles, actually we get a slightly different behavior. So the finer particles travel further. So shape has a big impact, and size clearly, because we're trying to separate by size. So we are currently analyzing, or the team are currently analyzing a huge amount of data that they gathered. On the right-hand side, you'll see a screenshot from a video they gave me yesterday. They were on a lunar gravity parabolic flight campaign last week, testing multiple versions of this system. You can see it's at lunar gravity here because Joe Dyson, one of the PhD students, you can see his hair is kind of gently floating there in the low gravity. But we've tested this now. We're testing our predictions for how we think this will behave under low gravity. And so we will come back when we have crunched through all of that data. But moving on to hydrogen reduction. So we've classified the particles, we've controlled the size. We're now going to do hydrogen reduction as one of the ways in which we can extract oxygen. Now, hydrogen reduction is one of those processes that has largely fallen out of favor. And the reason for this is that it is low yield. So if you put, if for whatever regolith you put in, you will probably only get about 1% yield of oxygen out of it. It relies heavily on the ilmenite content. So it's the ilmenite that is reduced in the regolith. And even then, the yield is pretty low. But hydrogen reduction has some great advantages. It's pretty straightforward compared to many of the processes that we use. It's relatively simple, it's relatively well established, and the temperatures that we need to use are also quite moderate, around about 800-900 degrees C. So it's got a lot of positives, but the yield is a problem. And you'll see at the bottom left, this is a large demonstrator. This takes about 1 kilo of simulant in the bottom left. So this is a system that we have at ESRIC that was procured by ESA, where we are currently modifying it so that we can use it safely in our labs because it's a pretty big piece of kit. So hydrogen reduction has its downsides. However, one of the ways that we believe that the process can be improved, the yield can be improved, is by using hydrogen plasma. So this is some work that's been done by a PhD with partnership with ESA. The PhD is called Marko Sikoric, and he has been looking at the fundamentals of hydrogen plasma reduction of thin films. So we can understand better the limitations, because it offers the potential for higher yield, but it is a surface-based process, and therefore there are limitations. So he's been using thin films and looking at the interaction with hydrogen plasma so that we can get a better understanding of at the fundamental level. So firstly, he did this with iron oxide thin films, and here he compared thermal hydrogen reduction with hydrogen plasma reduction. Looked at the energy consumption and found that the hydrogen plasma needed 6 times less energy to extract a microgram of oxygen. So actually the results are favorable. The hydrogen plasma, it's 6 times less energy. On the bottom right, you can see the thin film before and after interaction with the hydrogen plasma, where you can see the collapse of that thin film as the oxygen is extracted, and we end up with metallic iron at the surface of that collapsed thin film. But that's iron oxide. We're trying to reduce ilmenite, not iron oxide. So he spent quite a lot of time trying to develop an ilmenite thin film, and we ended up with something that's not quite ilmenite. So it's an iron titanium oxide. They called it pseudo-brookite, but effectively it's an iron titanium oxide. And same process. Again, we take the thin film, reduce it using hydrogen, and reduce it in plasma. And here we see the sample weight loss, you can see at the bottom, is significantly higher now under hydrogen plasma. So for this iron titanium oxide, the plasma needed 11 times less energy to extract the same amount of oxygen. So again, here you can see the collapse of the thin film before and after. So this is incredibly favorable in terms of energy consumption, but this is still a lot we don't understand. And we still need to convert this fundamental result into a system-based a prototype. So we need to go from this thin film in a reactor, into a prototype where we can interact the plasma with particles, and so that we can start to scale up this process. And this is our intended next steps for this project. And then finally, in terms of research, we're interested in not just oxygen, but also metal production. So if we look at what we're left with after oxygen is extracted from lunar regolith, we end up with metal byproducts. And the intention here is that we would like to use these for manufacturing. So this is a project that is being carried out by Timon Schild. He's looking at molten salt electrolysis. In molten salt electrolysis, we extract all of the oxygen. So with hydrogen reduction, we only extracted the oxygen from the ilmenite in the regolith. With molten salt electrolysis, we extract pretty much all, 96% of the oxygen that's in the regolith. And then what we're left with is some metal byproducts. And then the question is, can we use those metal byproducts in additive manufacturing? So here's the principle of the molten salt electrolysis. We use a calcium chloride electrolyte. We use a carbon. We would like to use an inert anode, but actually we use a carbon anode at the moment, so it's consumed in the reaction. We produce CO2, and this is what on the right-hand side you can see what the assembly looks like at the beginning. So we have a sintered pellet of simulant, the graphite anode, and this is placed in a calcium carbonate bath at about 900 degrees C. What we see is that we evolve carbon dioxide and carbon monoxide, as we might expect. And then on the right-hand side, you can see the metallic byproducts at the end of processing. And if you analyze those metallic byproducts, what you end up with is broadly a mess of alloys. So Timon published this in a paper. He did a full characterization. It's complicated. The alloys you get there's a huge range of different alloys of aluminium, silicon, and calcium iron in various different amounts. But broadly, what you see before and after is that the oxygen is extracted, and we end up with aluminium, silicon, calcium, iron, and some residual oxygen. So in the samples, we had about 3% residual oxygen. Now, the next question is, can we use this? So rather than taking the reduced byproducts, what Timon's done is taken the same proportions that we see here of aluminium, silicon, calcium, and iron, and then put those in a crucible and melted them to 1,000 degrees C to see if they melt and to see if we can use them in additive manufacturing. So on the right-hand side, you can see the melt that was produced by this ideal reduced material. And then he took this to Airbus and used their metal 3D printer to test whether we could 3D print. So we used a kind of ideal aluminium silicon wire with our ingot that was produced from this pseudo-reduced regolith to see if you could 3D print using our ingot. And in fact, the results were incredibly positive. So the aluminium silicon wire deposited very nicely on the aluminium silicon calcium ion ingot. And we can see the first layer actually on the right-hand side, the first layer melted into the ingot, and then we subsequently built the layers on top. So there's real potential to use the metal byproducts, certainly the ideal metal byproducts, in additive manufacturing. Subsequently for things like manufacturing of metal parts, for in situ assembly and repairs. And we are continuing this work as we speak. This PhD should come to an end in the next 6 months or so. So we can do this at a small scale. This is a 25-gram pellet, but the next thing is to take this to a larger scale. So now we need to go to 1 kilo scale. I showed you a picture of the 1 kilo hydrogen reduction system that we have in the lab, the demonstrator. In January, we take delivery of 1 kilo of simulant molten salt electrolysis cells, FFC cells. There's 3 of those that will operate in sequence, and that will allow us to test those 2 different process routes at similar scales, and also to produce more reduced material that we can work with to understand what can and cannot be done with the reduced metal byproducts. So this leads us to the last few slides of what we do at ESRIC. That gives you an overview, a fairly rapid overview of skipping across the disciplines of the kind of work that we're doing in ESRIC. We are also building up our labs, as I said. These are our old labs on the left-hand side. We've moved to new shiny labs now, but the principle's the same. We have a beneficiation area we have oxygen extraction, which has currently the hydrogen reduction system, but will be joined by the molten salt electrolysis systems in January. And then water purification we're doing with Air Liquide using adsorption. Next year, we take delivery of Europe's largest dusty thermal vacuum chamber. So this is 2.2 meters in diameter. This is being procured by ESA, will be operated by ESRIC, and is there for the community to use to test their technology in a relevant environment. And this will be followed at a later stage by a ground-based pilot plant. It's based on molten salt electrolysis as a core technology, and then the supporting technologies up and downstream of that. But just to finish off, I mentioned the incubator and the accelerator. Our incubator program is now pretty well established. It is open to any startup with a space resources concept from around the world. Our next call, that'll be our 6th cohort, will launch at the beginning of December. So if you have if you are a startup with a space resources company, let's say space resources idea, then look out for the information on our website or LinkedIn for the launch of the next call for the startup support program, the business incubator. Our business accelerator is in its first cohort. This is based on a 50-50 ESA co-funding model and is only open to ESA member states. We've just had our 2nd ESA and ESRIC Space Resources Challenge. So this is an innovation-driven challenge that we run with ESA. The first one focused on prospecting was completed a couple of years ago. And the second one just ran in the lunar facility at the European Astronaut Centre, where we focused on lunar excavation and beneficiation, so size classification. There's some great videos out there. So again, if you look at our LinkedIn, then you will find a video of the recent challenge, which was really spectacular. But finally, then if you would like to find out more about what we're doing, please join us in Luxembourg for Space Resources Week. Next year, we are running from the 4th to the 7th of May. The call for abstracts will open soon. Again, at the beginning of December, I think we're launching the call for abstracts. More importantly, the deadline should be early to mid-January. So keep a lookout for the deadlines there. But come join us because this is the largest gathering of the space resources community. So we had about 450 people, 470 people on site this year. And it really is covers all aspects. So science, technology, startups. We also have the legal sessions. So it's a really good overview of everything that we're doing in space resources. Finally, my very final points. I know I'm running slightly over time. I always like this picture of Gene Cernan covered in dust because really, if we go back to my mining days, it's not so dissimilar. We have a long experience of working in these dusty environments. The nice thing about space resources is that it gives us an opportunity to completely rethink and redesign our processes for extracting and using resources. So we're designing systems under significant uncertainty, and we are heavily constrained by mass, energy, water use, and complexity, but we're completely unconstrained from preconceived ideas. So we can look at different ways of separating particles by size. We can look at different ways of extracting oxygen and metals from lunar regolith. We can look at different ways of using waste byproducts to perform some useful function. And I think this is one of the genuinely exciting things about space resources. So thank you very much. Here's our team celebrating 5 years last week. But thanks very much for listening.
Thank you, Kathryn. This was an awesome presentation, and happy birthday, ESRIC, and congrats to everyone who's worked there since the beginning or joined since. You guys do some really cool work. I'm really happy that we got you on to present some of it. So without further ado, I am gonna jump to Q&A. The first one, how flexible is ESRIC in approaching partnerships? Do we have to wait for an official call to approach ESRIC to discuss ways of working together?
That's a very good question. We are always open to partnerships. As I said, we're sitting in a research and technology organization, so we're always open to collaboration. It depends. The answer to everything is always it depends. It's really unsatisfactory. It depends. It depends on how it is you are interested in collaborating. So if you have a startup, if you are a startup or you have a startup business, then we issue calls for the incubator. If we are recruiting, then those are listed online. If it's for research collaborations, then we're always open for discussion, but it obviously always depends on funding as well. So we're always looking for ways to support collaboration, as I think many of us know.
Great, thank you. Next question is actually one that I had. Are the three molten salt cells in series planned for January the same project as the ground-based pilot plant, or is that a separate project?
Great question. It is different. So the three molten salt electrolysis cells are part of a different project than the pilot plant, although the core technology for the pilot plant is obviously molten salt electrolysis. So you can immediately see that there is some transfer of knowledge and information. So what we are expecting is that the data and the experience that is acquired from those three multi-salt electrolysis will feed into the pilot plant. However, they are both separate projects, both run by ESA. And again, we are running the cells that we will acquire on loan. But all the data goes back to ESA, and they will use that to inform the pilot plant, however they decide.
Very cool, thank you. I don't see any in the Q&A. We're gonna wait for some, but while in the meantime, I have a question, and it's
Go for it.
incredibly non-technical. But I guess we don't get a lot of chemical engineers on here, and it is certainly a lacking group in this community, in my opinion. Um, what is your personal favorite? No, Ezric, just Kathryn. What is your favorite resource extract? What is your favorite lunar technology that's currently being developed?
Well, I would always say that you can never have too many chemical engineers. It is, it's an interesting one. When working in space, I'm just gonna not answer the question for a second while I think. But working with so many disciplines is always really interesting because you understand the different ways that the different disciplines think. So as you know, the role of the chemical engineer is to sit there and look at mass balances and energy balances. This is what we love. We love a mass balance. I love to know what my mass balance is and what my recovery is and so on. Aerospace engineers, very different, just mass. So I think the way in which the different disciplines think is really different, and that's always a joy to observe. In terms of what my favorite technology is, I'm a mineral separations person. I will always come back to beneficiation because that is my background. That's where I am happy. It's really, really difficult process. So anything to do with size classification or mineral concentration, I think that always makes me happy.
Well put. As a geologist, I tend to like the same stuff as well. So cool. Thank you. And again, yeah, uh, just a personal question. So, next question in the Q&A. What do you think to obtain a partnership with Sierra Corp in the same project, the molten salt electrolysis?
So currently, with molten salt electrolysis, the large cells that we will get, we're running at them through a contract with ESA in which like I say, we all the data goes to ESA. And then for any subsequent work that we do, I think we are always open to collaboration. So if there's ideas and opportunities out there, we would love to discuss.
Perfect. And yeah, what's that? I'm under the weather and not remembering right, but within the past couple months, we had Brant White from Sierra Space on presenting some of his molten regolith electrolysis and reduction. Oh, no, it wasn't MRE. It was wow, I am really in a brain fog today. It was carbothermal reduction. But
Ah.
so there, if you're interested in ways you could collaborate, you can check out that talk. So anyway,
Sorry to
yeah,
jump in and
please.
Jared, while you're talking, but anything that I think allows us to compare as well, direct across processes is really useful. Because one of the things we're really lacking is comparative data. So even though hydrogen reduction, like I say, is fallen out of favor, but even by comparing similar scales of hydrogen reduction and molten salt electrolysis side by side, it provides really useful information. We as an RTO, we have no commercial interest in either, in pursuing either. So it is in our interest to publish data and to show to the community actually how these things perform because they have advantages and disadvantages, and it's always a trade-off. There's no clear winner and no winner. So anything that we can do to improve the amount of data that is out there for people to use, I think is a good thing.
Agreed and well put. Um, Hi, David. David Bemis asks, are there other reduction techniques that you are considering, like mechanochemical methods?
Mechanochemical methods. Oh, that reminds me of they used to be I used to like with milling, you can do this kind of same kind of thing with chemical milling, comminution, reactive comminution type approaches. We are not currently exploring any others, so we are very much focused on hydrogen reduction, plasma enhanced hydrogen reduction, and molten salt electrolysis because there are so many that we could do, but I know that different research organizations, different companies have different expertise. And so I think rather than spread ourselves over, we're still pretty small and relatively new in research terms, then rather than spread ourselves over a huge number of different types of processes, we're focusing on the ones building up expertise and capabilities in the ones that we have. And then over time, we can certainly continue to grow.
Awesome, well put. And I see three in the chat, right, in the Q&A right now, and we're gonna cut it off at those three in the interest of time. because we could sit here all day asking you questions. Comment. This has been incredibly fun and insightful presentation. Thank you for sharing. Question. Coming from a U.S. academic institution, how are some of the ways to collaborate in terms of funding and research activities? That's a great question.
From research, from academic institutions, actually, there are bilateral agreements between Luxembourg and the US. This I do know. So also on that one, I have an answer. So between the Luxembourg Funding Agency is the FNR. We've got funding from the FNR, and I think is it NSF in the US?
Yes.
Um, yeah, there's bilateral agreements, so there are ways that that collaborative funding can be sought that way. Otherwise, it's quite complicated. But as long as if there's a bilateral agreement between countries, and there's at least there is something.
There's the mechanism. That's great. Useful for my own purposes as well. Thank you for that question, Shaspreet. Um, in what proportion your study are from Glasgow University studies on regolith?
So we haven't worked with Glasgow. I know they do some really excellent work and they've got their own dusty thermal vacuum chamber. So I am aware of the work that they do and they do some really fun work. We haven't worked with them to date, but we are always, like I say, always open to chatting. The community is relatively small and always really lovely. So we're open to discussing with Glasgow.
Awesome. Well, I'm gonna read this last question, then I gotta get a couple links to punch in the chat, and then we can call it. You briefly mentioned dust mitigation and airlock seals. Could you tell us a bit more about the work you are doing in this area?
Gareth, nice to hear from you. I know Gareth. He was when I was doing my postdoc, he was doing a PhD.
It
Anyway,
such a small world,
it's
isn't
a
it?
really small world. So we are not doing anything to do with the dust seals as such, but we're doing dust in enclosed areas. So we are looking at developing tools to support dust mitigation in enclosed areas in airlocks with DEM. Incorporating electrostatics, but also using extended reality. So we're looking at the two different approaches. So this is a PhD. It's the guy with the longish hair in the screenshot of the parabolic flight, Joe Dyson. So he's been doing a lot of simulations. But I'm always happy to talk about this with you, Gareth.
I keep losing my Zoom window trying to do other things here. Well, Kathryn, that is the last one we have in the Q&A, and while I feebly attempt to multitask in pulling up this link I forgot to grab, I want to thank you for giving this talk. For those of you who do know, this series is hosted by the American Institute for Aeronautics and Astronautics Space Resources Technical Committee, and specifically the um, the Education and Outreach Subcommittee, of which my co-host Joe Kenrick and I are the co-chairs of. So with that, I am almost to where I need to be. I am so sorry for the delay here. It's not letting me sign in. Interesting. Weird error. Anyhow, I will just post what I can get right now in the chat to everyone. I just put the link to the YouTube channel where this recording and all of our other recordings are available for your viewing pleasure. There is a repository where we upload these slides, and Kathryn, if you're not able to share for any reason, that's fine, but if you can send me your slides after, great. And I can upload them to an AIAA internal service called Engage for people to download and view as they see fit. Again, if you and your organization are comfortable with it, no obligation. Um, that said, I see we are 1 minute past time, which is a bit better than usual. So well done, Kathryn. Um, so everybody, in the U.S., I hope you have a good Thanksgiving break. To everybody outside the U.S., if there's any holidays that you're celebrating or anything at all, I wish you the best. This is our last webinar for 2025, so we will plan to see you in January 2026 to ring in the new year. Stay tuned for announcement details on that, and that's all I got. So, Kathryn, thank you so much. It's always a pleasure.
Thanks, Jared, for the invitation, and happy Thanksgiving to those who are celebrating.
Awesome. Thank you. Bye.
Thanks. Bye.